Alright, this is my first time using this app, so we'll see if it turns out alright. I've just been trying to think of better ways, more definitive ways to explain the idea of standard deviation as it applies in real-world situations. And it's just kind of, the more I thought about it, the more I realized that it's really crippling to try to define standard deviation with how little definitions or terms, keywords that we know about the things involved in statistics. All we know are mean, sample, and mean, median, mode. Or sorry, mean, mode, median, interquartile range, that sort of thing. Nothing that really helps us with the idea of standard deviation, or more importantly, the idea of variation, because standard deviation, as we talked about, is just the square root of the variance. I said variation, excuse me, the variance. So nothing that really helps us get to variance. So let's see. Switching a slide. Yeah, I want to take a quick detour as far as want to make sure we're keeping the definitions different when we're talking about samples and population. Just a quick thing, I didn't mention it in class, but if we're saying that something, if we're like a value, say the mean or the standard deviation, those are not the only two, but those are the two of the big two. If we're talking about those in reference to a sample, we said that those are statistics, or a statistic. So if we're talking about sample mean is a statistic, whereas population mean, if we happen to know it, would be a parameter about the population. And a couple of notation things here. The sample mean is denoted with the X bar, and population mean with the Greek letter mu, which is just the funny looking U. Sample standard deviation, little s. Population standard deviation, lowercase Greek sigma. And this one is only marginally important. Most people can keep track of n and big N, but we might say that we have a sample of size n versus when we have a population of n people or n cars, etc., etc. All right, moving on. Okay, here's a quick example that I think should help us out here. And I was trying to write it all ahead of time, so I wasn't trying to write and talk. And I've got a 2-year-old in the other room, so I didn't know how it was going to work out here. But if this is the number of car sales, new car sales by a new car salesman, a new employee, his first 6 months, no other months he's worked there as a car salesman. We're just talking about just him, just his sales. And his sales for the first 6 months, respectively, were 2, 0, 3, 5, 3, and 11. So we need to make sure we know if we're talking about a sample or a population. That is key. It's marginal and it's usually obvious. And your answer would only be slightly different if you were mistaken. But it is important. In this case, because we have all the information for the number of months, those are all the months he's been a car salesman that he sold cars, and that this is a population standard not a sample. So we're looking for mu, not x bar, even though they're calculated exactly the same way. So we need the sigma, or not, excuse me. We need capital sigma of all the x's, the sum of all the x's there over big N, which is the same thing, just how many there are. So add those up, you get 24 over 6 or 4. Now here's where I kind of want to introduce an idea of a definition that we don't have, and we don't have until chapter 5. And you don't necessarily need to know it, but it really helps bring the point of standard deviation across. If I were to tell you that you picked one of his months at random, and I'm stretching I'm stretching our abilities here by saying maybe the next month, even though you absolutely should never do that, you can't extrapolate. But if you were to pick a month at random, and say like one of the 6 months, you don't know which one it is, one of those 6 months, you want to pick it at random, what would be the safest bet to be number to pick? Like if you were playing Price is Right and you wanted to have the closest number to how many he went, although not with the restriction of being over, if it was just the absolute closest number. So if you were playing some kind of game and you were asked to pick how many cars you think he sold for a month, one of these 6 months, you just don't know which one, and you wanted to have the best odds of winning that game or what have you, what number would you think would be the safest to play as far as being closest, and most likely to be close to any other number? or excuse me, most likely to be the closer. I don't know how to say this. It's most likely to be very close to whatever number it is picked, and the odds of it being very far away from the actual number. So say if it was, if you said this number and it was 11, it was very far away from 11, then those odds are very slim. Next slide. Okay. The idea I'm trying to get across here is something. Well, going back to that example. If you were to pick any number that you thought that would be the best way to go, you would go with 4, because that's the average, or the population average. No matter what, in theory here, but whatever he sold, whichever one of those months he picks, it's going to have to be somewhat close to 4. Some more than others, but that's the safest one to pick, because if you pick 4, worst case scenario, you get 0, or even worse, I guess 11. But there's only 1 out of 6, that you got 11, so you're 7 off. But if you pick 11, then any of the other months, you're 6, 7, 8, 9, 11 off. And there's, a 5 out of 6 chance of that happening. So that 4 is just kind of the safe bet. That's what you would expect him to have got. On a much larger scale, if it was a much larger group, or if this was a sample, and you wanted to know the expected value. It's quote-unquote the expected value. Oh, pen. Is what we call it. And it's a definition we learn in chapter 5. The expected value, I'm not going to full-on define it here, but it basically, it says, if we pick an element from our group at random, whether it be a sample or a population, if we pick one at random, and what would we expect its value to be? Just randomly, or with no knowledge about it, we don't know anything else about it. Like if you were asked to pick a lottery ticket at random, what would you expect the cash value to be? Well, you'd expect it to be very close to 0. There's a chance it could be worth money, but the mean is probably, somewhere in the neighborhood of $1 and change. Who knows? Or the expected value of what's a good one? If you were asked to pick a length of pregnancy of a random woman, you would expect, your best bet would be to go with 40 weeks, and that might not be true. I assume it is. You get the idea. It's the value you think would be right. That's it's the average, is what it is. It is the average, but not more than that. Any value that's in this group, you would expect to be that number, even though they aren't all that number. That would be your best bet. So I guess we get this, maybe best bet might make sense, although we're not talking about betting at all. So hopefully that makes sense. You don't need to know this, but it is denoted capital E of X, so it's for future reference. We're not using it right now. I just want to use the idea of it right now. So if we were taking these each of those car sales values, and I hope I remember them, because if I go back, it's going to mess this up. I believe it was 11, and there was a 5 in there, and there was a 3, 2, was a 0, and a 3. Is that up to 24 or 14? Yeah, those were the values. So, if we want to kind of come up with this idea of standard deviation, or variance for that matter, what we should really come up with is more an idea for each individual one of these. So for just the value 11, I don't want to, it looks like a 0. So for just the value 11, how does that vary against the expected value? So if we pick a month at random, we say to pull it out of a hat and it's got the numbers of his car sales, we're like, okay, we're expecting that to be 4. And you open it up and it happens to be 11. How did that vary from what you expected? And that would be, your actual, oh, I lost the pen. That would be your actual minus your expected. That's how things, in general, that's, again, we're going to really use this a lot more officially later on. But if you're expecting one thing and you get another, and these are two numerical things, two number-related things, we can actually calculate how bad you were off. For instance, if you expected a paycheck that was $500, but it was only $450, then there was a variance, or they varied by negative $50. Conversely, if you got a $50 bonus, you had a variance of positive $50 for just that one. I'm trying not to say variance. I'm trying to say vary, because although I'm talking about individual item variance here, we don't really talk about them as items. We talk about the whole group. So I do apologize if I slip and say variance in reference to one data point. I'm trying to say how it varies. The same thing goes for 5. If you wanted to know how it varies compared to if you expected it before, you got 5, how that varies. What would be actual minus expected? And I think what I'm going to do here is I'm going to move the 11 to the bottom so I can let that actual minus expected be kind of a header. So we expected 4, right? So actual minus expected would be 5 minus 4, and then 3 minus 4, 2 minus 4, 0 minus 4, 3 minus 4, and 11 minus 4. It's important to note that it doesn't matter if it's expected minus actual or actual minus expected, even though right now it's going to be sign important. In the end, it won't be. And so this is going to come out to be 1, negative 1, negative 2, negative 4, negative 1, and 7. So what does all that mean? What does this 1 mean up here on the row with the 5? That means that if we take what we expected it to be, if we compare what it actually was, if we are pulling this month at random out of a hat with the number of how many cars he sold that month, we expected it to be 4. It's actually 5. There was a variation, I'm trying not to say variance, of positive 1. Same thing goes down. If we expected it to be 4 and it was really 11, there was a of positive 7, or negative 1, negative 2, negative 4, negative 1, 7. And notice that if you add all these up, 1 plus negative 1 is 0. Negative 2 plus negative 4 is negative 6, plus negative 1, negative 7, plus 7 is 0. So the sum of all of these, and I wish I had more room at the bottom here, the sum of all of these, I guess I'll put it over here. Let's see if I can't. I'll probably end up erasing it after the fact. Here's what I'll do. I'm going to erase this up here. I do apologize, this is getting kind of long, but hopefully it's helping, and hopefully people actually watch it. And hopefully, obviously, my voice recorded. So, if we take these and we sum them up here, and this is super unofficial, if we summed up the actual minus the expected, that would be 0. And that's kind of what you would think here, because if you took all of these and you added them up, what have you actually done? You've added up, in this case, you've actually added, or you have the sum of, actual minus expected. Well, that would be 5 minus 4, plus 3 minus 4, plus 2 minus 4, plus 0 minus 4, plus 3 minus 4, plus 11 minus 4, which is really this. 5 plus 4, and I'm going to end up erasing this too. I wish I would have had room at the bottom. I didn't mean to write that line. 0 minus 4, 3 minus 4, 11 minus 4. You could regroup these slightly and say that this is the first numbers, 5 plus 3 plus 2 plus 0 plus 3 plus 11, and then minus, that's what? That's 6 4s, right? 6 times 4. Well, this right here, that's the top half of our calculation for population mean. Population mean was 4 equals 5 plus 3 plus 2 plus 0 plus 3 plus 11 over 6. So if we solve for just the numerator, we multiply both sides by 6, well, then we get 4 times 6 is equal to this. Well, that means that this is 0. So obviously it ends up being 0. So how can we take that and use it in our advantage? And I do apologize, I'm going to be erasing on something that I've been using here, but I really want to keep the left half of the screen. I don't want to have to rewrite that. And I don't want to have to break it up on 2 different slides. So, 1 second here. Also, the eraser is super small. There's no way to change the size. Alrighty. Okay, so what does that mean that it's equal to 0? What does that mean for us? Well, it means that it's not a good measure of center. It's not a good way to tell how the set is, because they're always going to be 0. So that doesn't tell us anything about the data at all. about the population, about the sample. Just like the analogy where I was talking about distances. You wouldn't add up to a positive and a negative distance. That wouldn't help us out here. We don't so much in math actually use the absolute value function, or in real math, because it's not, I don't know how to explain it. It's just not something we use. The only real way we have of taking things and making sure that they are always positive, or always non-negative, if I'm being technical. 0 is not positive, but it's not negative, so it's okay. The only real tool we have to make sure that things are always not positive, or take a group of things and make them not positive. Make them not negative. Make sure they are positive. I'm going to say positive, I mean positive or 0. The only way we can absolutely make sure all the elements that we've just done this thing to are positive is squaring them. For instance, if you take negative 2 squared, you'll get positive 4. If you take positive 2 squared, you get 4. If you take 0 squared, you get 0, which is not negative, I know, or not. It's not positive, but it's not negative, which is what we really want. So that's kind of our friend here, and we can square and then square root later, although not quite in that order. And it's a process known as normalizing. I think I've seen it called standardizing, but I'm pretty sure just normalizing. You're familiar with it mostly from the distance formula. y2 minus y1 quantity squared plus x2 minus x1 quantity squared. You're familiar with it most like this, where this is really a summation of just two things. All right, so it's a little, maybe not quite as confusing without the summation symbol and the square root, but that's really what we're doing there. But right now, all we want to do is we just want to square these things. See, okay, if we square these, then what happens? So if we just take this actual minus expected and square it, well, that would be 1 squared is 1, negative 1 squared is 1, negative 2 squared is 4, negative 4 squared is, positive 16, negative 1 squared is 1, and 7 squared is 49. Now, these things are all positive. They're definitely not going to add up to 0. Well, we want to know about the group here, so let's go ahead and add all these up, and then we'll sum. And I don't have the room to write it, vertically, but we've got 4 and 16 make 20, 1 and 49 make 50, so that's 72. So now we've got this total square of this actual minus expected. We took this actual minus expected value for each one and we squared it and added them up. This is the total square, and I don't want to use the word variance, the total square difference between what we expected and what we actually got. The way these two numbers varied. We squared it and then we added them all up. So this is total. Suppose if we wanted to average that out, well, we would divide by how many elements we had. In this case, 6. So in this case, we end up with, 12? So now we've got 12. That's saying that if we have any value, okay, if we have any value, then we know that it is gonna be, well, it's a square here. So it's kind of hard to really relate this back to it because we're talking about in squared here. But we know that it's the standard. I don't want to say standard yet. We know that the average of this square value is 12, and they're all positive. So we can say 50, at least half of them, or half of them are going to be 12 or less. That's kind of the idea here. All right, and then we're going to take that and extend it a little bit further. I'm going to get a new slide finally. Maybe. All right. So right where we were talking about, we've taken this, we've squared it. So that's, we're talking about actual minus expected. That's actually not no different. That's exactly when we were talking in class And all the one big example I did was a sample, and I wish I would have done one as a population instead. But that's really no different than these headers here. Mu minus x, or x minus mu, or xi, if we will. And then mu minus xi, quantity squared. So we had those values. They were, I think, 0, 2, 3, 3, 5, and 11. And, oh, I didn't mean that to be mu. It was supposed to be I. Or xi, excuse me. These were our xi values. Our individual xi. The mu, of course, was 4. So mu minus these would be, whatever they were, 4. I think I get them backwards here, so it's end up being, they're all going to be, flip signs. But again, it doesn't matter. So we took all these values and we squared them. Just doing the same thing, different title, different headers here. I just want to write 16 squared. Don't want to do that. 4, 1, 1, 1, 36. All right. Oh no, that's not right. Sorry. There's no way to go back in the recording either. So -7. That wasn't right. This is 49. Still, if we add all these up, the sum of all those. Remember, this is a fancy way of writing sum now. Mu minus xi quantity squared. The quantity is outside the sum, so we square, then we add up. That's what that means. That was what came out to be 70. Or 72. Oh, man. 72. Then what we did was we divided that by the number of elements. So what we had was sigma mu minus xi squared all over 6, but in this case, 6. I'm going to write 6 is equal to capital N, just for reference. And that came out to be 12. This right here, this guy, that is the definition. This is the definition of population variance. All right, we square these things, we add them, and then we add them all up, and then we average it out. That is variance. That is average variance, because each one of these values, the 16, the 4, that's the individual. We don't call it individual variance because we don't want to confuse it, but really that's how much variance that one item had. So the variance of the population denoted with sigma squared. Sorry, not sigma. Sigma squared. Is the average of those things. You add them all up and you divide by the total number there. And then standard deviation is nothing tricky at all if you just remember that whatever variance is, standard deviation is just the square root of it. Very rarely is there a time where you're just going to calculate standard deviation somehow magically without really getting the variance and taking the square root of it. There'll be a lot of times where you'll use standard deviation as opposed to variance, but you could just, write in the square root of the variance instead of that. This, of course, was population variance. And then, I didn't leave myself a whole lot of room here, but look. And the square root of sigma squared, that's the square root, is equal to sigma. And that's the standard deviation. Population standard deviation. Let's see if I can't squeeze it in over here. Sigma is equal to just the exact same thing, but a gigantic square root over all of it. Sigma mu minus xi quantity squared all over capital N. And that's population standard deviation. Hopefully that makes a whole lot more sense. Yeah. Let's see just a real quick bit on sample. All right, so sample standard deviation is everything, all the calculations, all the reasoning, all of it is true until you get to the part where you average it out, where we average it out with population. I'm going to write sample variance, and then in parentheses standard deviation, because we usually only care about standard deviation, but we get it from variance always. Anyway, so everything was the same except for with if we go through the same process, when we're doing it with population, when we got the sum of all those things squared, so I'll write it in terms of sample here. This would be x bar minus xi squared. So we got this here when we added them all up with the population we were talking about, mu. And then we averaged it out by dividing by how many elements there were in the population, capital N. So you would think we do it with little n here, and most people get confused as to why we don't, and we do n minus 1. And the reasoning is not quite straightforward, but it's something along the lines of this. We're talking about how much variance this sample has. A sample taken at random from a group, and we assume that sigma squared is somewhat close to, I'm terribly sorry, backtrack. This is not supposed to be sigma squared. We're talking about sample variance. This is little s squared. We're assuming that sigma squared is somewhat approximated by little s squared. But there's just as good a chance that, if this is true, if s squared is approximates theta squared, these two outcomes are just as likely. S squared being strictly greater than sigma squared, or s squared being less than sigma squared. We don't particularly like this possibility, the s squared being less than sigma squared. The reason being is because we know s squared approximates sigma squared. All right. If s squared is possible to, if we have this thing that we said it's approximating this, and we got, it's a 50-50 shot here that s squared is going to be less than, based on our sample, that's going to be less than the real sigma squared. Then we're going to make faulty conclusions, or not necessarily faulty, but flimsy conclusions that our population has this smaller standard deviation than it really does, which can be catastrophic. For example, if you're talking about medical stuff, medical pills or whatever, you're talking about the success rate, goods versus bads. I'm really bad at specific examples. Say people that died or something, and your sample has this really small standard deviation of people that died or something. I don't know. It causes something that can cause people to die. Then you're going to make this conclusion that, oh, well, my mean's right here, way on the green side. Let me see if I can't draw like a picture here. So you say this is, this is the bad line. This is, death or whatever. I don't know. And you get your sample mean to be here. You might find that your s squared, if, your s squared, and I guess in reality s, because we deal with s, is x bar minus s is here. You're way ahead of the bad. But if this is true, then x minus theta might be down here, or x bar minus theta might be down here, down in the bad. So you might be saying, oh, we're good here. We're golden. Let's put this on the market. People are going to be fine, etc., etc. But this is a 50-50 shot. You don't know really what you're saying. So we correct that. We correct that by, one second, by adjusting how we define sample standard deviation to strictly make it larger. And how do we make something larger? Well, we make its denominator smaller. Right. And I can go into a whole big long thing about how, the bigger your sample, the closer it is to, because we're talking about variance, but the issue we're having here is the variance of the variance, which we're not going to go into, but the bigger your sample, the less impactful that is. It's something I think we should learn about in a couple chapters called degrees of freedom, but it's not important right now. So we make sure, or we can't really say make sure for sure, positively, but we make it more likely that s squared is greater than sigma squared, because we're really not looking for an approximation of sigma squared or sigma. We usually want an upper bound, per se, an accurate upper bound. Obviously, you can say upper bound's 1,000,000, but what good does that do? You want a useful upper bound. So that's why we make it n minus 1, because anything 1, if you look at 1, when the denominator is smaller, then the fraction is bigger. for example, 1/3 is greater than 1/4. This is 0.333. This is 0.25. Greater than. So that's why it's plus or minus 1 in the denominator there, even though you're like, but it should just be n. That's why. And other than that, everything's exactly the same between the two. What we're going to get into shortly is a new slide. What we're going to get into shortly, and I'm about to go get him, is dealing with these sort of distributions here, where we want to say, okay, if this is our x bar, or mu depending, then we want to know how much of the data, or population I guess, is within a standard deviation. So it's a lot like, the interquartile range there, how much, 50% of the data is between those two. But this is a lot more, a lot different. It's not just bulk data. This is the data that is literally, super close within a standard deviation. I'm struggling to come up with an example here, but you might, let's see, if you are working at an airplane, the way their luggage is loaded, they have to be, they have specific weights for, specific weights and distributions here for, where'd the eraser go? Why'd you just leave me? Eraser. There. Okay, now it's stuck. I can't erase. So, new slide. Alright, so you got an airplane, a poorly drawn airplane at that. There's your airplane with the wing here, and there's the other wing there, and they got the motors and what have you. And windows. These things have a very specific way that the weight has to be put in these. If you put too much weight down here, it'll weigh the tail down, and it'll be very, very hard to land, because the tail will be very heavy, and it'll want to scrape the ground. If you put it too hard in the front, it'll be very hard to take off. If you load one of these completely wrong, the plane could very well crash. Matter of fact, I very briefly worked at an airport loading aircraft, and the person that was in charge of, I think they called it weights and balances, the person was in charge of telling the pilot where all the baggage was, where all the weight was. If they made a mistake or lied or something, and the pilot was flying on faulty information, and that plane went down because the weight was wrong, because he had faulty information, the person working at the airport gets charged with every count of manslaughter for every one person on the plane. Involuntary, of course, but so it's serious business. I mean, it's not it's not just whatever. You have to be within some range. So let's say that the I don't really know how to put it here, but say the desired let's see, desired weight distribution, X bar. And what I mean by that would be weight in rear minus weight in front. That would be your weight distribution. It's a very crude example. It's a lot more into that. And let's say that you want 0, and I know that's probably not true. I'm almost certain you want way more in the back. But anyway, let's just say it's 0 for argument's sake here. Obviously, it can never be exactly 0. Not every plane's always going to be exactly 0. You'd have to have counterweights and sandbags, and it would just be unbelievably impossible. So obviously, you have to have some kind of room to work with here. And that's true, and people have done all these calculations, blah, blah, blah. There is this standard, that has a standard deviation here of what the optimal safety, et cetera, of the weight distribution is. So you would say that, let's say that S in this case is 500. Who knows? I don't know. Then you would say if we are x minus 5, or not x, excuse me. This isn't an example you'd actually have to do. I'm just trying to, prove a point. X bar minus s, which was negative 500, or x bar plus s, which is 500, then you would say if you're somewhere between negative 500 and 500 pounds as far as the weight distribution, 500 more in the rear, 500 more in the front, then we're good to go. But if you were like more than 1,000 off, then you might be like, whoa, we're not good to go. Something like that. I mean, a lot more goes into it. And this is kind of what I just did here is a very watered down example of something we're going to do way later on called a confidence interval. But that is completely different. That was about it. Most people probably either understood Z as far as that goes, or will understand it with just a little bit of practice. I think the standard deviation was what really threw people off, and then you have to know standard deviation to really use Z. So hopefully this video / presentation was helpful. Hopefully it turned out all right, and hopefully I can get it uploaded and on the Angel there. Also, my son has not just been sitting in his high chair this whole time. He's been eating, and then as soon as I started talking, he started screaming at the end, and then when I stopped, he'd stop and laugh and look at me, and as soon as I start talking, he screams again. So he's fine. He's just being what a 2-year-old. It's what 2-year-olds do. All right, well, post up on the discussion board if you have any questions. Email me. Hopefully we can talk amongst ourselves, make sure everyone gets a better understanding here. All right, have a good week.